Hello everyone, my name is Lan. Welcome to our presentation. This paper is about a method to estimate a probabilistic representation of the implicit surface of 3D objects. I will firstly introduce our motivation and method, then show some results comparing with other popular reconstruction techniques. First, I'm going to talk about our motivation. On one hand, from common visual SLAM or structure from motion algorithms, we get a set series of optimized sparse points, and on the other hand, we get a set of dense noisy points that come directly from depth images or optical flow. The aim of this work is to provide a probabilistic representation that allows to fuse these sources of information into a dense continuous model. I will use Stanford Bunny to show a pipeline step by step. Our approach takes as input sparse key points reconstructed from visual SLAM methods and fuse them with noisy dense point cloud including normals obtained from depth images. To reduce computational complexity, we proposed skeletonization submapping to divide the whole dataset into pieces following the topology of the object. Point cloud will contract using Laplace Pietroni operator. We can pick any node as root node for this tree structure. While doing this, the algorithms keep tracking of the association between the nodes and the points. Based on this information, datasets X and Z are divided into n meaningful submaps, which are easy for hyperparameters to optimize. To deal with discontinuity, we allow conditionally independent overlapping between submaps. Then, an efficient GPIS model is trained per submaps using the corresponding points and normals. A Gaussian process model is used to infer the mean and the covariance at any testing point using those two equations. To reduce computational complexity, we used a recently proposed DSKI algorithm to achieve faster inference for Gaussian process implicit surfaces, our in-short GPIS. DSKI uses an approximate kernel function, reproject the input data into a grid generated by the inducing points, enable fast kernel learning and prediction with derivatives information by implementing interpolation. So next step, the key points belong to each submap are fused with the corresponding prior implicit surface. The update of the mean and covariance values of the GPIS are performed as follows. Gamma Z representing the implicit surface value for key points. H is a spatial observation matrix, and R is a diagonal matrix. Then, next step, using the forward propagation to prevent discontinuity, each submap should be conditionally independent. For example, submap SI is conditionally independent with SI plus 1 given the overlapping part B, so on and so forth. The mean and the covariance equations will be updated after forward propagation. Overall, we called our method DSKI-CI fusion. I will talk about an illustration in a cross-section of Stanford Bunny at testing points showing sparse to dense fusion and forward propagation. After using DSKI-GP, testing points produce a probabilistic implicit surface prior per submap. In both directions, outside and inside, the variance values increase. Sparse to dense fusion reduces the uncertainty inside of the submap. After forward propagation and fusion, variance values at the junction edge of this submap have significantly improved. Also, it is very clear that the mean values inside are negative and outside are positive. If the large mean values and variance values have been taken from the submap, the result has some testing points around the surface. I will talk about a quantitative evaluation of the surface reconstruction with Poisson algorithm from different sources. reconstruction directly from the noisy dense points, we can observe an inaccurate mesh due to the noise. And for figure B, the result is quite smooth without details. The reason is points are accurate but sparse. As we can see from figure C, the bunny is a little bit fat since the filtering keeps lots of the points with low uncertainty. After forward propagation and fusion, the points will converge towards the real surface. The final bunny is very similar with the ground truth. Then all the bunnies are colored by distance error from A to D and colored by variance from E. The distance error is from Poisson mesh to the ground truth. It can be seen an improvement on the surface reconstruction and the reduction of the error across the whole body. To show that our approach can deal with noise robustly, we use different noise added to the dense point cloud. DSKICI fusion filters the most amount of noise, keeping it constant even with an increased noise variance. Our approach can also yield good surface reconstruction from partial data missing. In order to test our algorithm in more challenging scenarios, the real-world data of the teddy bear public dataset is used. As a quantitative evaluation, we average the closest neighbor to smooth the normals and get the histogram of the angles between the original and smoothed normal for each reconstruction. It shows that our method produces normals with less noise than OB-SLAM and MVE. Finally, in order to show that our algorithm can cater for larger amounts of data, we have included the journaling caves, which contains more than 1 million points. The first figure shows the skeleton of journaling caves. The second figure shows initial noisy point cloud with normals colored by submaps. The last figure shows DSKICI fusion final point cloud. Here is a video showing our final mesh of a cave tunnel from the entry to inside. This table shows a dataset summary for Stanford Bunny, Lamb Caucus, Teddy Bear, and journaling caves. Journaling caves is quite challenging in terms of the amount of points managed and fused. Finally, the contributions of our paper are as follows. We present a probabilistic and accurate reconstruction given a dense noisy point cloud and optimized sparse points. We proposed a novel skeleton submapping method following the topology to generate conditional independent GPIS. Our approach can deal with large-scale non-structured data. Challenging real and simulated datasets are used for evaluation. Thank you for listening. Have a good day.